everybody for your patience. Now, finally, there are my slides. Let's start. First of all, announcements. The typical, please work on your homework. On top of that, I just got feedback from the TFs that a lot of you did not put a lot of effort into the essay in the last homework. And I do realize it was the last question of the whole assignment, but I also have this feeling that some people don't take it seriously, like if they're asked to write an essay. But these, like you're going to see the next homework is out already, I think. Yeah, people are working on it. It's going to ask you to do a slide presentation to your boss. These things are not in there to annoy you. They're there for a reason. So this is the third year of the course. And the first 2 years, we realized that people were not putting enough emphasis on very good storytelling. And we didn't push that during the homework, and what this resulted in was bad final project presentations. And doing good presentations, not only for us and for the sake of your grade, but when I try to look for TFs for this course, the first thing I do is I write the very best students from the year before. And a lot of answers I get is, oh, I'm sorry, I can't, I would really like to, but I'm working as a data scientist now. So you're going to have to go for interviews. And one really good thing you can do is like point them to GitHub, right? And say, this is the final project I did. And by the way, here's a really cool YouTube video summarizing the whole thing in 2 minutes. So you also have to learn to present the cool things you discover. So please take these parts seriously. I also realize there's a lot of time pressure, most probably, when you come to question 4. So try to maybe start a bit earlier so that you can actually invest time in persuading your boss to mail or mail not any orders. Okay, next topics. I see this lecture a bit as a wrap-up of the supervised classification part. So we talked about a lot of classifiers. There are actually some really cool things about the random forest that I still wanted to emphasize. And then our emphasis so far has mainly been on classification. Joe last time already hinted a bit that you also can do regression with a lot of these things. In my experience, a lot of people tend to do regression in their final projects. So I wanted to show you how that actually works with things like a decision tree or KNN. Then we're going to talk about best practices in data science and in machine learning. So how do you choose your model, what to do with imbalanced data and with missing values. And then I'm not sure how the time will work out. If we don't come to this today, I'm going to do this next Tuesday. So I want to talk to you about recommender systems, collaborative filtering, content-based filtering, like on Amazon, right? People who bought this were also interested in, maybe you want to buy this too. So that's what recommender systems are about. So first shows the recap about the random forest. So we said we had the single decision tree and it overfits. Then came the idea of doing bootstrap from your sample and train multiple trees, use the randomness to create different trees and then average them all together. And that was bagging. And then on top of that, we said we're not only introducing randomness by doing the bootstrap sample, now also at each split, we don't show all the features to the tree, we only show a random subset of those. So those are the two parts where randomness is induced into the random forest. And we said the idea behind bagging is that you have multiple trees and each tree alone tends to overfit, right? That's the big disadvantage of a single decision tree. It's really fast and nice, but it doesn't generalize so well because it overfits. So we train a lot of overfitting trees on bootstrap samples and then average to hopefully get the smooth decision boundary that works better. So because we are actually using this high variability and the high variance of the decision trees, all trees are fully grown. There's no pruning in the random forest typically. And you have the two parameters to tune: the number of trees and how many features you show with each split. Which of the two parameters is actually the difference between bagging and random forest? Yes? The number of features, yes. That's the big difference. The random forest is the bagging idea plus the random subset of features. So if you take all the features, if you make that parameter here, the number of features, your whole set of features, you just have bagging. So random forest error rate. So the error the random forest makes depends on the correlation between the trees. We actually do not want them to be similar. We want them to be different. But on the same side, you also want each single tree to be a strong predictor. That's what the random forest lives off, right? So you would like your single trees to be strong, but you also would like them all to look different. And this is what you do when you tune this feature parameter. If it's very high, you increase the correlation between the trees, but you also increase the strength of every single tree. Now that typically needs some time to digest what that means, so I made an example. So this is a total extreme scenario that you're not going to encounter. Let's just do this for fun and to see and get a bit more insight and intuition. So here I have a label vector y, right? So these are the labels for my classification problem. And here's my data matrix X. And now what I did is I copied the labels as the first feature. We can actually train the perfect classifier on this. There's one feature where that perfectly encodes the label of the class. But the rest is complete random noise, junk. So that's this extreme example. We have one feature here that is the actual label, and all the rest is junk. And let's say this guy is fairly big, 100, 1,000. So what would a single fully grown tree learn? If I just do now a single decision tree and give it this data set, no bagging, no bootstrapping, no random features, just the pure decision tree, what would it do?
It would use the X.
And which part? It would use the X. So X is this whole matrix here, right?
So the first column.
The first column. That's the decision tree when it tries to decide the split. It tries each single feature in turn, right? Looks how good the Gini gain is and takes the one with the best gain. Now, splitting on these features, each individually, is not going to go very well because it's just noise. Splitting on this feature is going to give it a perfect split in one go. Right? Can you see that? So just a single decision tree that gets to see all the data, all the feature, is just going to grab this first column and do a perfect split with the first try. So it's actually going to be a stump. There's only going to be one split in that decision tree because it's going to find that feature right away. It's highly unlikely that there is a random column here that actually does equally well to the first one. So that is what the single tree would learn. It would actually only have one split, so not very deep. So what would bagging then do? How would it differ? What would bagging do? So now I take this bootstrap sample from this. So I sample with replacement the different rows and build an X1 and an X2 and an X3 matrix. What would it learn? Yeah?
Would it learn the same thing?
It would learn the same thing. Pretty boring, right? So each tree in there, although it gets a random subset of this relation here still holds. So it would still learn, aha, I only need one split on this feature because also the trees in bagging get to look at all the features. Now let's take the random forest to the extreme. And let's say, now the random forest only gets to see a subset of the features for each split. Now let's take that to the extreme and say I'm only going to allow it to look at only one feature at each split. I can do that. Is that random forest going to work? Yes? So you need to speak up. Yeah?
Sorry, isn't it somewhat dependent on how many times you run
Yes, it's dependent on how many times we run it through with one feature, but the how many times is actually determined. Random forest has fully grown trees. So it's going to do split, 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 split until all the leaves are pure. But you do have the right intuition. What is going to happen with the decision tree that sees a random feature of this for each split? Yeah?
So it's going to be sullied by a bunch of noise. So it will, so it's going to do a poor job of specifying because it will average. It
So
will be using. Sorry.
no, it's right. It's right. So both intuitions are right. The single decision tree that only sees one sub-feature for each split is not going to have much of a chance because most of the times I'm just going to show it random noise. It still needs to decide on a split somehow. So it's going to split somewhere, right, split the points, split the points, split the points. Now, as we said, the decision trees are not restricted. So it's going to keep doing that until it has pure leaves. Now, if this is a million random things and not that many data points, there might be trees that actually never ever see the first column of this matrix. Right? If you don't have that many data points and just noise, you can overfit like crazy. Right? You can just split, 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 split until each single data point somewhere had its own cell. You're going to have a super fragmented space and you're only going to have one point in each cell. That's what's going to happen. So this is the idea now. So each tree then, especially the trees who maybe just split, 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 all that they learned was a fitting to the particular noise they saw from this bootstrap sample. So they're not going to predict well at all because it's just based on noise. So in the random forest, if this is taken to an extreme now, because each single tree is so weak, the random forest is going to be very bad, right? The performance is going to be way worse than that of a single decision tree. It's going to take hours to compute and then give you a wrong result. So this is what is meant here about choosing this feature in a way that your single trees are strong. If I make it that small, if it only sees one feature every time, the single tree is not going to be very strong, except for those trees that get lucky and encounter this, right? So now if I instead increase the number of features the tree is allowed to look at, then it gets stronger, because the likelihood that it actually hits on a feature that is meaningful is increased. So you want that max features, typically it's the square root, right? But the way you want to tune that is dependent on the noise you expect in your data. So and we had the other extreme, if it looks at all the features, then we have bagging, right? And then we said we actually need to do bagging in this extreme case because they're all going to be the same. So choosing a lot of features makes the tree strong, but all pretty much the same. Choosing few features is going to make them more independent, but if each single tree only learns junk, then averaging junk still gives you not that good of a result. Are there questions about this? No. Okay. So then there's something very neat that the random forest comes with. There's a reason it's so popular and well used. Like with the support vector machine, you need to tune more, right? You need to choose your kernel and your parameters for the kernel. And with the random forest, you only have the number of trees, and typically you can see the error converge, so that's not that hard to tune. And you have the number of features to split on, and the default actually works pretty well in a lot of cases. And it has this other nice thing that is the out-of-bag error. So what does that mean? We have our samples here, our data points, and I can create a bootstrap sample from this, and then train the tree. This is now not the training of the whole forest. I'm literally speaking of the step where you just tune one tree, train one tree. So we saw before that means so bootstrapping is sampling with replacement, right? And we saw before this number here on slides, that's the number of points covered from our original data set. That means there are about 30% of the whole big data set that we didn't use in the training of this single tree. Over the whole forest, over all of the trees, we're going to use all of them. But just for the training of this single tree, we have about 30% of our data that this tree has not seen, which means we can kind of use this to do an estimate of our test error. Right? So during training, 60% or 65% of the training data were used. And now I used the out-of-bag samples, the samples that didn't make it into my bootstrap sample, and compute a test error. And then for each tree that you trained in the forest, you combine these test errors, and that gives you the out-of-bag error. And that is something that you can use to just very fairly quickly plot and see how the error goes down with the number of trees. So this is a very useful thing often to look into. It's also something to be careful with, though, because it looks very similar to cross-validation, right? So it looks like a valid, and Brayman actually advertised it as a valid evaluation method. He said, out-of-bag error, can't go wrong, just use that, you don't ever have to do cross-validation again. But it's still measured during training, and a lot of people empirically found that it's too optimistic. So I would not recommend reporting the out-of-bag error as your final prediction error. You should still use cross-validation. Nevertheless, it's a cool thing if you just want to gain fast insight. Do I have enough trees? Does this make sense at all, what I'm doing here? So, and I actually found there's a lot of confusion about this, and I found this post on the Kaggle forum. So Kaggle's, Joe mentioned before, is a platform where you also can go register and do competitions, data science competitions, machine learning competitions. And it's fun. It's also hard. And they have these very nice forums where people interact with each other and say, like, oh, I have a real problem with this. How do you do that? And one of these was a person who was very frustrated because he was trying to estimate his prediction error before he submitted. So Kaggle has a test holdout set. So he submitted, and then the error he got from the system was much worse than what he computed for himself. So he was thinking he would do better. And he was frustrated because this was happening all the time. And he was wondering why. And it turned out he actually did not do cross-validation. Because he said, this seems redundant. The random forest already has so much randomness inherently in it with the bootstrapping and the random splits. Why should I do cross-validation on top of it? And the answer is, because without it, it doesn't work. So this is really, you should do cross-validation regardless of the method you use. Because it's very easy to run into overfitting, and that is the most useful tool I know of to battle that. Okay, variable importance. So the random forest has the out-of-bag error, and it can give you an estimate of how important a variable is. And it has two methods to do that. And one, again, uses these out-of-bag samples. So what you do is, you use these out-of-bag samples that are not part of the bootstrap sample, and then you predict the class for these samples. And now comes the trick. You randomly permute the values of only one feature. So you basically make one feature useless in all those data points. And then you do the prediction again and see how much your accuracy decreases. If it doesn't decrease that much, then that feature wasn't useful, right? If scrambling that destroyed your whole prediction performance, then that feature was very useful for the classification. So that's the idea. Here's the famous apples-orange example with the color and the shape. Right? Think about this split here. Now if I scramble the color, it doesn't matter at all, right? The split, if I split on shape, yeah, because they're both round, I get a crappy result. And if I split on color, I'm fine. So if I split on shape, I get a crappy result, but if I would scramble these points, my result would still be crappy. If I split on color, I get this nice result, but if I would scramble my points, it wouldn't work at all anymore, right? So that's the idea here. So that's your measure for variable importance. There's a second version that looks at the Gini improvement in each split. So that also decision tree can give you. And here's the comparison of the two from the Hasty machine learning book. And you can see this is the randomization one, so this is using the out-of-bag samples, and this is the gain in Gini performance. And they do look different, right? This is more uniform, this seems more strict, more discriminative in the feature importance. For me, most of the time, I only care about the ranking, and this is not exactly similar, but pretty much. Basically, the upper 10% here, also the upper 10% there. So I normally go with this one, but I'm not sure. Maybe you just want to try both and take the union. So I'm going to go over to regression now. Any questions about the random forest in general? No. Okay, let's talk about regression. So first of all, just a reminder, what is the difference between regression and classification? I had this actually happened in a final project about star ratings, right? And you only can give whole points. So it was a rating from 1 to 5. So they said, classification problem, 5 classes. That works. Yes?
Well, regression would assume an ordinal scale.
Yes.
So 1 to 5, maybe 2.2 has an interpretation between 2 and 3. But if you have categories and you're trying to classify them, like red and
okay,
blue,
yeah.
then somewhere in between red and blue is.
So regression would assume a whole scale. That is true. It's harder to have regression only predict integers, but you could round. The scale part, yeah?
Oh, sorry, I was just going to say regression preserves like the distance between, say, a 1-star to a 2-star.
Yes, that's the one I was really going for. Yes, the regression preserves the distance between the labels. A classification problem doesn't care that 2 stars are closer to 1 star than to 5 stars. It doesn't take that information into account. It's just if it's 2 stars and you predict 1 star, that's a misclassification error. If you would predict 5 stars instead, it's also just a misclassification error. The error would not be weighted according to which class they end up with. In a regression problem, you have this notion that the error is typically squared or something, right? And the distance from 1 to 2 is smaller than 2 to 5. So KNN, we talked about classification. We have our k nearest neighbors, and we just do the majority vote. That is very, very easy to adapt to regression. What would you do? So now everything that would happen is instead of having red triangles and a blue square, I would have numbers here, right? My regression numbers. So what would you do now? Yeah?
Maybe instead of having the labels be square and triangle, you give them numeric labels and then ask for like the mean in some circle or something like that, or a property about
Yes.
some function of the numbers in that area.
Yes, you just average those. Right? You have your k nearest neighbors, and now they don't have classes anymore, but these would be actual numerical values. You just average the 3 closest ones. So you can, now the choice you have is how to do the averaging. You can just average all k nearest neighbors, or you can weigh them according to their distance to the point you're querying, because closer neighbors maybe know more. That is something you can also do with the classification. Yes, question?
Yeah, I was wondering if you have like 6 classes in the problem, and there's maybe one class 6 and one class 1 nearest to the k, and you average at 3, but that makes no sense. Or 3.5. How would that work if you have multiple classes and averaging?
If you have multiple classes, how would that work? Do you mean the majority voting now?
Yeah.
Oh, if you would handle this as a classification problem, you mean, with the star ratings?
You said you were taking the average of the ones that were closest, right? And if you have classes, for example...
Oh, right. So for classification, but that's then regression, right? For classification, you take the majority vote.
Yeah.
Okay, and then if you, all that I meant to say, sorry, was you can also weight those votes. You could say that a point that is closer, let's say you have a scenario where you have 6 classes or whatever, right? And your k nearest neighbors are by any chance distributed in a way that one neighbor is right here, right? And let's say your neighborhood is 5, and then you have 4 guys all the way out here. Whatever, right? So then you might want to assign weights and say, well, I do a majority voting of the classes around here, but let's make this guy actually a different class. But this guy is really, really close to the point I'm querying, and those guys are further away. And even though I can't choose k that small because I overfit, I maybe still want to take the closer ones better into account. So you still do a majority vote, but you don't listen equally to every neighbor. So in classification, you need to have some form of majority. In regression, you can average. What?
I think maybe you're still considering the them as classes as opposed to real numbers, where it doesn't make sense to average them. So
Yes.
you wouldn't use this method if what you wanted in the end was an actual class.
Yes.
That are separate.
Yes, so that is the difference between regression and classification. In classification, you want the majority vote, and you want one class as output. And averaging, it's like easier when you think about actual class labels, right? Oranges and apples. Doesn't make sense to say it's the average of an orange and an apple somewhere in between, like, I don't know. You could use that as kind of a score on the classification, because it means you're not that sure whether it's an apple or an orange, but in the end you would still convert it to a label. Whereas in the regression, you actually are after a number. So if you have only the closest neighbors are 1 and a 5, doing the average actually is not the worst idea, and is a valid outcome. So here's an example of k nearest neighbors regression. So we have this curve here that we want to fit, and this is uniform weighting. So this is just averaging k is 5 here. So here we're just averaging the 5 nearest neighbors to each point we're querying. So if you query some point here, you look for the 5 nearest neighbors. 1, 2, 3. Not sure how close they are. I'm bad with judging distances from here. But apparently the average was somewhere here. And you can see this is a discrete thing here almost, right? It looks very discrete. Like you have this jump. It's the step function going on. What is happening is, as you go querying from 0 onwards here, you have your 5 closest neighbors, and this is where the next neighbor from the right side is closer, and the first guy from the left disappears, right? That changes your result. So there are a lot of queries here where you actually end up with the same k nearest neighbors, and this is why you get the same value. Whereas here, we do a weight. So we weight each point by the distance to our query point. And you can see it looks smoother, but it also looks weird a bit. And you can see it has these hakama hanging thingies, right? And the more important one is you actually get all the outliers here. This does not look like a good regression solution to me in this case. Why does this happen? So you weighted by 1 over the distance, right? If I query directly at this point here, although it is an outlier, is so close to the point I'm querying, it's basically overruling all the others, right? It's shouting the loudest. So we basically nearly only listen to this one point there. So I did try, I actually did this. And this is something else. So we saw this extrapolation idea, right? That's what you do a lot with linear regression. Maybe you remember the XKCD, where he's putting the number of weddings, I think, against years. And before it's 0, 0, and then after 1 year, she has 1 husband. And then he does a line and extrapolates and says, you better stock up on wedding cake, because in 10 years, you're going to have 10 husbands. So this is hard to do with k nearest neighbors. You can't extrapolate because you don't have nearest neighbors down here. But good idea if you maybe want to fill in the gaps here or smoothen that curve. So I did fiddle around with this a bit. I was surprised, like normally I thought the distance weight is squared. It's 1 over the distance squared. That's what I thought the default would be. It's not. In scikit-learn, at least in the version I have at the moment, it's just 1 over the distance. And that is why it gives these ziggy-zaggy thingies still a bit. So the moment I squared this, it actually got smoother. So you might want to check this out when you look at the k nearest neighbors regression function. It has this argument, weight, and that takes uniform, distance, or a function that you define yourself. So you can put whatever distance in there that you like. Yes, Christian?
Sorry, maybe I'm just missing something really basic, but I'm confused about what you're predicting here. Are you splitting classification?
No, we're doing regression now. The question is what we're predicting. What I'm predicting is, for example, the value here for 1. I don't have a data point for that. But I still want to get a sense of what the value would be for 1. So I kind of need to compute where this would be. That's what we're predicting.
Okay.
And we want the whole continuous spectrum here. I want to be able to query any number between 0 and 5. And then the function tells me a 4.5 is a, I don't know what.
Right, but 1 is not, it's not a classification, right? It's not where you're going and saying, what are the points around you, like you're trying to...
No, so we're not doing classes anymore, but it's the exact same idea at work here. Before, in that problem here, it was just in 2D, and you queried your nearest neighbors and asked for which class are you. And now, when I want to query here, I ask which are the 5 closest data points to this guy.
Right.
And then I average the numerical values of those, and this gives me the point here. So the idea is really the same. It's just averaging numerical values instead of doing majority vote on class labels. Cool. More questions about the KNN regression? Yeah?
So here, this is sort of one-dimensional, where on the board you had your different classes, 2 dimensions. There are 3 classes, this is a 1D, if I understand.
Yeah, so this is just 1D because it's easier to show for me. I thought this would be more intuitive. There is no, so the dimension would just be the number of features you have in there, right? It's just hard to draw, to make this idea of a regression clearer. But there's nothing restricting you of doing this in higher dimensions. Yeah?
And I'm assuming that the data comes from a sine wave with noise.
Yeah, I think this was generated. It's just a wave with noise. So the other thing you can see here, if you think about which regression method to use, it's really hard to prevent the sloping from happening. So you want your points to be fairly close to each other, I guess, when you use k-nearest neighbors regression. So decision trees can also do regression. Like all the classification methods we talked about, most of them can do regression. So the decision tree here, that is what we talked about, right? You do all the different splits, each only on one feature, which is why you get axis-aligned splits, and then you end up with these nice partitions in your feature space. And then when a new point comes in, you just look into the partition and again give the majority vote. So the idea now is the same as in k-nearest neighbors. If we make this a regression problem, we don't have classes anymore. I was a bit lazy. What I should have done is color these differently. That was actually my try to show this in higher dimensions. So normally this would be light red and very red, right? So these have numerical values on them. And then I look, and the data point comes into the cell and gets just the average vote of the data points that are in its cell. So it's really the same idea, how to go from classification to regression. So again, we average over all the points in the cell. And with the decision tree, we have one more thing to take care about. We said the splits are determined by Gini impurity or purity. We can't use that anymore, because in regression you don't have this notion of a purity. What you instead can do is you minimize the squared error to your labels. That's the typical thing done in regression. So this is the example now, again, just with our sine wave idea. So this is a decision tree doing regression with a max depth of 2. So if I put a decision tree with the maximum depth of 2, I have 4 cells, right? I have 4 different splits in my decision tree. And you can see those here. Right? Maybe this was the first split, so I ended up with one half and the other half. And here's the second split and the other one. So I have 1, 2, 3, 4 different cells in my space. Does this make sense? I guess this was the first split. You end up with all. So if I would just do a decision stump, I would get all these points averaged into one line, and then all the other points on the other side averaged into another line. Right? It's a crappy, but it's a regression solution. Now I can do more splits and regard all the points on this left side here, split again, and get this additional step in here. So these points average here, together with these guys down here, give this value, and then all of these guys averaged give kind of 1.0. That's the idea how to do regression with a tree. So this is just step 2. Now we can go further down, and you can see if you allow more degrees of freedom for your tree, so you split more, and that is when you start to fit the outliers again. So also for the regression problem, your decision tree, unfortunately, is suffering from the same thing it suffered before. And the cure is the same as before. It's to train a whole forest of trees and average them. So the random forest also can be used for regression. We just, again, train multiple trees in parallel and average them. Just be careful, because the standard defaults for regression are different from the ones for classification. It's trained a little differently, right? Not using the Gini index, but the squared error. And it's using these different defaults. One default that surprised me, I actually have to check this again the more I think about it, but I think the max features, so the number of features it sees in each split, is in scikit-learn defaulted to the actual number of features. That would mean it's actually doing bagging. I have to check this again. And as I said now before, it's actually using the square error and not the Gini purity. Questions? Cool. Support vector machine. Hard for regression. Do not just take the distance. So support vector machines are always a bit tricky, because the original design was purely for classification. And we said the output basically is +1 and -1. It's even hard to get a real, like you can kind of interpret like your decision boundary. If you have your maximum margin and then you're separating hyperplane, right, somewhere in there, you can interpret the distance between your data points and that separating hyperplane in a way, right? Remember the oranges and apples? The oranges that are way away most probably look like very typical oranges, and you're very sure of your classification. The ones that that are here maybe actually are an apple. So there is an intuition about the distance to the hyperplane, but the score you get is not a probability. I just wanted to emphasize this again. There's nothing bounding this, and it doesn't even have units. You don't even know what the scale is of that distance. So, but nevertheless, you can use SVMs for regression, but you have to change the whole optimization problem again. Remember, I very briefly showed this scary equation where you like minimize everything subject to all these constraints. That minimized misclassification in a way, and again, you kind of use the square error instead. What's more interesting is what is actually happening, and remember our parameters in the kernel and the C for the slack. This is what I wanted you to show. Remember the slack variables where we said, like, if you have a misclassification going on, let's take that guy away, make this a circle, and have an X on that side. The SVM doesn't like that. It would normally do with the original formulation. It would just go here and change the entire decision boundary, right? And we said instead, we can introduce these slack variables and have the C parameter that allows a point to have some slack to the decision boundary. And if we make C really small, we introduce more slack and get a more stable decision hyperplane. So for regression, you have the same notion, and what the slack does is kind of defines a band here. You see a kind of upper and lower curve over my wave here. It's actually really hard to see, isn't it? This dotted line in here is the actual regression solution. So what happens is, dependent on my C, this band here gets wider and wider. And this max margin idea translates to regression in a way that the SVM is trying to find the smoothest solution kind of within this band. And you see the dotted line here maybe very poorly, but this is the regression result again. So the dotted points here, that's the same. The dotted points here are the original function. The black guys here are the support vectors, and this is the regression prediction by the support vector machine. And what you can see, the influence of the C is very similar. You get less support vectors. Right here, I only have those 3, and you get a smoother prediction because this band here is wider. So just as an intuition for you, if you want to use this, how to think about the C. Then again, this is now yada yada because boosting is kind of the same, right? We talked about the random forest boosting. You again have trees. You average them just in a weighted manner. The boosting idea was you have the points that did not get correctly classified. Why did I? Oh, I only have the overlay, sorry. So green here is the very first step of boosting. You only have your first classifier trained. So you have your points here, you train your first classifier, and you get the green line. And then you see that it actually doesn't get these outliers here. So you put more weight on them. It's not outliers, these data points. So you put more weight on them, right? And you train the next classifier and say, please pay special attention to these guys that the other one didn't get. So the next one is going to try harder to classify those right, and you do a weighted average. And you see here the red guy is after 300 classifiers, and it gets closer to these points. It's still a smooth prediction, and it gets closer to the extreme points. So also boosting can do regression. So that was my whole part about regression. Any questions left? Oh.
Yes, with band regression, you have your output is it more concretely tells you something about the functional form. So, for instance, y might be twice y or something like that.
Yeah.
Do you forfeit the ability to interpret things in those terms when you use KNN?
Yeah, you don't really learn much about that function, I wouldn't say, no. The goal here is to get good predictions. It's not so much about insight. The question is how to gain insight from these regression methods as you might from linear regression. It's hard. Like, I think that's one reason why statisticians normally go to linear regression, right? To get that insight. So then I'm going to go to best practices now. Put all that regression stuff aside. Still think this was really important to go over because, as I said, I think 90% of the projects last year were regression. That doesn't mean don't do classification. It just seems that our imagination running wild is easier for it to come up with regression problems in the real world. So if you don't understand this joke, you have been spoiled way too long with high-level programming languages. In the very beginning, there was this go-to command, like code said, were numbered lines, and you could actually say go to line 30 in the code. Like that were your if statements. It was like if true, go to 30, if false, go to 50. And there's a whole thick paper written by Dijkstra called Go to Considered Harmful. So if you don't know it, praise yourself lucky and don't go there. Oh, this is even, oh no. This is even crappier than I thought. Unfortunately, I couldn't find this picture outside of a video, so I tried to make a screenshot. I did upload the PDF files. Please look at home, because on the other hand, this is now very nicely summarizing what I wanted to say. So there are a lot more lines in here. And this is actually showing results from several Kaggle competitions. Remember that website where you can do projects? And this is the time of the competition here, just scaled from the whole time is 1.0, so just the time evolving. And this is the difference to the best result achieved in the competition. So it's not some kind of score, because they all use different scores. Instead, it's the percentage of the best result achieved when the competition was over, so you see all the lines converge to one. What you see when you open those PDFs at home, or what you can already see now, is the easier ones. And you can see this here is darker, so there were a lot of lines here. They have progressed very fast. So that's your first just out-of-the-box random forest giving you a great result. And then after that, you start fighting. You fight for every single 10%. And that's a very, very typical thing. I've seen that a lot happening. Like in my PhD group, like a lot of machine learning problems are going to behave like that. Then there are the harder ones, where people really fought almost linearly. And there actually are also some where there was maybe a total eureka moment, or somebody else joining the competition, because there's even one line that goes like this and whoosh goes up. But that rarely happens. So I would say most of the time you're actually in this area here. So hopefully you're going to make progress in the beginning very fast, but then you'll have to fight and try to squeeze the rest out of your prediction performance. And this is a thing to keep in mind, especially as a data scientist, when you speak to people in the application domain. That is something you will have to do. And they will ask you, what can you do? And can you do this? And can you do that? Right? And they will ask you to get a perfect result. And you're going to try because you want to make them happy. And you're going to fight for these guys. But if you have a high salary and are costing the company a lot of money, you actually might argue with them how much this improvement is still worth. So this is really something you should keep in mind. And then take it from Yoda. Do or do not, there is no try. And what I mean with that is, especially if you say, yes, I can do that, and then 4 weeks later you come back and say, well, I tried. No points for that. Right? So under-promise, over-deliver, I think is one of the biggest things a data scientist who does heavy machine learning work should like, that should be in your bones, like really. Also for PhD students, regarding your advisors, it's good advice there as well. Even with the final projects. Even when your final project is even too ambitious, we might ask you to tune it down. But also there, I mean, I don't mean do the simplest thing possible, right? You need to do something challenging. But it's better to say, I'm going to do this and have a realistic estimate of what you can actually achieve than to overpromise, saying like, yes, I'm going to do all these great things, and then you have to come back and say, well, it didn't work out. Because one of the biggest things in machine learning, the trickiest one, is it will be harder than it looks in a lot of problems, especially when you do something regarding vision. It's getting a lot better now with the deep classifiers. I wouldn't recommend using deep learning in your final projects, though, because it's a time sink. And I would, if you haven't worked with it before, I would be very That's also the reason we don't teach it now, because I'd be very, very hesitant to believe that people actually get results then by the end. So with a lot of things in machine learning, it actually is harder than it looks. Because at the beginning, when the customer or your colleagues from the application domain come to you and say, please, can you solve this? It looks so easy, right? Of course, that should be in the data. And of course, you can already see that in your first plots. But then when you actually start training, what looked so easy was your mind filling in those percentages here. And you get here, and you're not really happy with the result. And you have to fight really hard and a long time to try to get up there. So again, it's this under-promise idea. When you see it and you think it's really, really easy, don't say that aloud. Say, I think that might be hard, but I think I can do it, right? Go and try first how hard it really is, and then give feedback. That also means, as a data scientist, it's very good practice to know your application. I work in a field that is very biology-inspired, right? I do reconstruction of neurons, and I know about the biology, and I can see the electron microscopy images and tell you that is a mitochondrium, that's a synapse. I can't do that as well as a biologist, but I've seen computer scientists just trying to segment these images with state-of-the-art methods without learning anything about the images and the microscopes. And they actually did build things that work. And then I told them, well, it's only going to work for that one data set you have. That moment, the biologist goes back to his microscope, all your effort was in vain. Because they highly overfit to the staining procedure, to the microscope use, because they didn't know what was going to change with a different data set. So you need to know your application. For this reason, how much do you overfit to the data set you actually have? Also in terms like the random forest, the support vector machine, all these classifiers we discussed, what we don't discuss that prominently is the majority of your work you're going to spend on feature design, right? Those apples and oranges, if you only put weight and shape in, you're going to have a really, really hard time. It is you who has to come up with this idea to take the color. So this is also why you need to know your application. You need to get a sense of what features might be useful. And do I maybe just take the maximum of this column in my data frame and put it in? Something like this. So you also need to know what zero values are. I had a summer project with REU interns doing predictions for an oil consulting company. And there were zeros, like this timelines of oil production, there were zeros in there. And we didn't know, was that just not measured, or was the oil barrel turned off? And that's very important, because if it's turned off, right, it's still keeping all its reserves. Whereas if they just don't measure for 3 years, then we might actually miss data. So what do outliers mean? Do you just throw them away? Are there measurement mistakes? Or are you at the CERN particle generator and they're really, really interested at the cases that look different than everything else? And where do your labels come from? Also very, very important, because most labels are generated by humans. And there's uncertainty attached to that. In image segmentation, humans, once they decided that's a valid edge, they tend to really be quite accurate if they make the effort. I had another colleague working with pathologists, people in hospitals who decide over life or death, right? They're the ones deciding this person gets treatment, chemotherapy, or deciding, well, no, we can't do anything anymore, or deciding they're healthy, right? They're the ones who make that call. They had 30% disagreement, just because they only look in a light microscope and say yes, no. And they actually didn't agree that much. So even if one person says they're absolutely sure about this labeling, it's good if you can have 2 or 3 persons doing labelings and seeing how much noise is actually in your labels. Because your classifier won't ever do better than that noise. It actually also doesn't need to do better than that noise. So sometimes it's a very good thing to have. And we typically use the term ground truth very freely. The labels are made by humans and can have mistakes. What you should do is ask 5 or 10 humans, if you can, if it's not too expensive, and try to get a consensus label. And that is, if you're really, really strict, that is called a gold standard. not a ground truth, because it's not absolute truth. So if you read the term gold standard, that's what it means. Then also good practices, document, document, document. And I actually mean foremost for yourself. You're going to come back in a year and have to read what you've written. And you have to make sense of it. So find a method for yourself, what works for you, from pen and paper, lab notebook style, to OneNote, to GitHub pages, what works for you, document your things. And then, of course, for others who might have to use your stuff. And commit, pull, push, repeat. We all know that one, right, from the homework. So, but the actual best practice I want to talk about is the machine learning part. How do you choose what to do? So you're a data scientist in the company, and the colleague comes to you and says, here's the data chunk, go. And you do EDA, and you decide there's an interesting problem in there, and you have a machine learning problem. And scikit-learn has this nice diagram that you can take with a grain of salt and just as this decision idea, right? If you have less than 50 samples, don't start. The first thing you do is try to get more data. So do you have more than 50 samples? Do you want to predict a category, or do you want to predict a quantity? So these are the different types. Yes gets you to classification most of the time, and no. So if you want to predict the quantity, then you're going to do regression. Those are the two different parts we talked about today. So if you want to predict a category, so you have a classification problem. Is your data labeled or not? Hopefully it is. Then you can do classification. That's all the stuff we talked about so far. Clustering here, unsupervised learning is going to come in a few lectures. So this is what we talked about so far. And you need enough samples here. Then you can go for the more fancy classifiers. If you have very little samples, you try to restrict your variance and maybe only use linear methods. And then with regression, you have your typical regressors here as well. So there's this notion in our head that different classifiers are good for different things. And this is why I wanted to do this with you. So you're the data scientist, and I give you data sets of different sizes. Hopefully have an error. Oh no. Yeah. This, of course, is not my laptop now. Let me try this. Can't zoom in. There. So let's try this. I'm going to tell you. So this graph here is... Oh, no. Great. Is that done? Don't try to make it worse. Great. So all I wanted was... let's do the whiteboard. So what's my x-axis there? Number of features? No. Samples. So we have samples here, and we have features here. The reason deep learning methods are so well used now is they're actually somewhere way up there. So I'm going to... So deep learning is all the way up in the upper right corner. It needs a lot of samples, but actually itself extracts a lot of features. So it's kind of somewhere up there. K and N. Where would you put K and N on this diagram? What is the thing? Yes?
Probably not very many features relative to
Probably not many features. And what's even more important with K and N?
I guess it would samples.
Yeah, also the... Sorry, yeah?
We discussed that the complexity of the
Yes, we said k and n is inherently slow with prediction if we have a lot of sample points. So we don't want that many samples, and then your answer comes in. If I'm restricted in the number of samples I want to use, I also need to restrict the number of features because I somehow have to deal with the curse of dimensionality. Right? So k and n is somewhere fairly down here. So then we have, what else stuff? Support vector machine, maybe. That's also a fairly easy one. Think about the curse of dimensionality and support vector machines. What's one of the great things? Yeah? It's low feature number? You want to have a low number of features. No, you actually can have the opposite. Support vector machines, remember this whole kernel trick it even can deal with? So support vector machines are extremely good to deal with a large amount of features. Yeah?
You also mentioned this advice that someone, or something mentioned that you should have at least 60,000 data points, so it's also for big samples.
Oh, the 60,000 are for deep learning. Sorry. I talked to Jan de Koon once, and he told me he wouldn't start deep learning under 60,000 samples. That's a lot more than the typical data set size was 5 years ago. So support vector machines actually are one of the very few classifiers who can still give you kind of good results if your number of samples is smaller than the number of features. Shouldn't be much smaller, but you actually can try. So just to emphasize this a lot, I'm going to put the SVM up here. What else did we have? Decision tree, single decision tree. Yeah, we're not putting that one on there because you shouldn't use it. I can't think of a problem at the moment that I would still tackle with a single decision tree. So let's do a random forest. So the nice thing about the random forest, computational-wise, is it slow or fast? With large data set, the complexity. For k and n, we said the complexity is really high. What is for the random forest? If your data set is large.
So it's much more efficient?
It's much more efficient. Where are my CS205 students? The random forest is embarrassingly parallel. Right? Each tree can just be grown independently of all the others. The moment you have your bootstrap sample, you don't care about all the other trees in the forest. You're only going to train your one tree. Doing training, doing predicting. Those data sets are coming in. The moment you have all the data for your one tree, you don't care about all the rest of the forest. That one tree can make its one prediction. All the others can do it in parallel. And then you just need to aggregate the results. So it's really efficient for large data sets, and each tree is also good. I'm just going to finish this here now. But then you need kind of enough features to be discriminative, right? But it won't be as good as a support vector machine if you have really high dimensional spaces and only very few samples. So let's put the random forest somewhere in here. So I think this is a very good way for you also to review what we talked about and to see those classifiers are not all equal, right? And it actually depends on your problem and on your situation which one you want to use. So let's talk a bit about cross-validation, and then I'm going to go and close the lecture. But cross-validation is such an important concept. I already mentioned it during that Kaggle competition remark. And we talked about it fairly briefly so far. So we have our training data, the validation data, and the test data. So you want to have 3 different data sets. Right? You have to be a bit careful with the terminology, validation sets. I've seen papers that call the test data the validation data, and they actually don't have a validation set. That might be because they don't have any hyperparameters to tune. Right? If you never tune any parameters, you get your data, and before you even load it, you say, I'm going to use a random forest, 300 trees, and the default for the split criterion. Right? And you're never tuning anything, then you only need your test set. And some people then call the test set validation set. So when you read a text that somebody else wrote, be mindful what they mean when they say validation set. Yeah, so that's about the meaning. Then the part of cross-validation we talked about was this 5-fold cross-validation. So I only have my training set here. That's what you typically see when cross-validation is explained. You see your 5 folds, right? And for each fold, you split your data into 5 different chunks. So you split it once into those 5 chunks, right? And then you take one chunk as the test data, you train your model on the rest, you do the prediction. You take the next chunk as your test data, you train on the rest, you do your prediction. All the way through, you get 5 different arrows, right? That gives you a nice plot with an arrow bar. Now, what you could do instead to tune your parameters is you actually do not take this as test data, but you do it as validation data. Right? You put your validation data here, and then you use these 5 folds to estimate whatever parameters you want, and then you have your test set out. Now we're back to our problem, which is that we wanted to solve by doing 5-fold cross-validation in the first place. The reason we do this complicated 5 folds is if you only split off the test data once, you're dependent, you might have been lucky doing that particular split. And this looks at all the data in turn. But now we're kind of having this problem again. There's only one test set. So what you can do instead, let's skip over that one, is this is the actual nested cross-validation. So what you do is, in one of these here, this is the test set, this was the training set, and I only put the first step here, where you do these 3 as training, and this is validation. But what should happen internally is this. You chop off your test part, and you do an inner cross-validation loop, where you do training set and the validation set. You have your different folds, and then in the end, you aggregate that together and have your test output. Does that make sense? You're basically doing cross-validation inside of cross-validation. You're doing one cross-validation to tune your hyperparameters, and you do the outer cross-validation to get a sense of your prediction error. The reason people don't like to do that is you already get a notion, right? Those are nested loops. That's going to be insanely expensive if you have a lot of parameters to tune. That's one of the reasons, I think it's one of the few things that actually have a parallel implementation of in scikit-learn, which I heard is a bit buggy in the moment, but it used to work in the past, so I hope it's going to get fixed soon. And then there are a few insights. So now you not only get one hyperparameter estimate, right? At the end of this, you have 4 different ones. So let's say you train your SVM. You want to tune the kernel parameter, C and gamma, and you get one result for this fold, one result for this fold, one result for this fold, and one result for this fold. Now, what do you do? The problem is it depends a bit on the parameter you're choosing. You could average the results from there, or you could try and see whether, if you just look, one of those was particularly good, then you might again run into this problem that it was just a lucky split, right? So maybe don't do max or min, do more something like aggregation over the different folds, averaging. And if your hyperparameters actually are all over the place, the estimates that you get here, you must probably have a problem, because the result might be very, very sensitive to this, And it might be an indication that your folds here are not large enough, that you don't have enough data points in there. So what you would do is you would need to do even more folds so that the test chunk you chop off that you're not allowed to use gets smaller and smaller. So you can pay off with computation for that. And the other thing to take care of is if the best parameter you choose in the end is at the right border or left or whatever, right at the border of your grid search, then you need to widen the window and go again. Right? You don't want the best parameter to be at the border. I actually think I'm going to close with this, and then maybe you can think about cross-validation. The slides are already up, so you can look a bit at them, and then we're going to do further stuff on this on Tuesday, because I think it's really important. Have fun. See you Tuesday.